Here we're going to tackle a fairly complicated problem that involves a tank. And this is a 100-gallon tank. Initially contains 100 gallons of sugar water. The concentration of sugar is 0.25 pounds per gallon. So basically that means that if there's a quarter of a pound per every 1 gallon, that means for 100 gallons there will be 25 pounds of sugar in there initially. Suppose that we add sugar to the tank at a rate of p pounds per minute. So we're just adding raw sugar, no liquid, into the tank. And the sugar water is removed at a rate of 1 gallon per minute. So then we're draining the actual liquid inside of there, and we're doing that at a rate of 1 gallon per minute. The water in the tank is kept well mixed, and we want to know what value of P we should pick so that when 5 gallons of sugar water solution is left, the concentration is 0.5 pounds per gallon. So first of all, we need to define some variables. We need to figure out what it is that we're actually trying to model with this differential equation we're going to build. We are looking at time passed, and because our units seem to be in minutes, it makes sense to keep it in minutes. And the amount of sugar in the tank is what we want to keep track of, and that's measured in pounds. So what we do know is that flowing in, we have p pounds per 1 minute. So keep in mind that our differential equation, dy dt, has to be the change in pounds divided by the change in minutes, and that is the change in pounds divided by the change in minutes coming in. P is a constant, but we don't yet know the value of that constant. We want to figure it out so that we satisfy a certain situation. What we know on the outflow side is that inside of the tank at any given moment, we don't know how many pounds of sugar there are exactly because that's going to vary over time. But we can say that there are y pounds of sugar inside of there. And then we need to figure out the volume. Well, so we're going to assume, and normally in these problems we do, that if there's no liquid coming in, that the sugar doesn't actually create any volume displacement. Now that's technically wrong because you know that when you add a pound of sugar to water, it definitely raises the volume of it. We're going to assume that the only thing that could raise volume is going to be the amount of water being added. So that means that initially there are 100 gallons inside the tank, and every minute, so this is really 100 minus 1t, where 1, the coefficient here, represents the gallons per minute coming out, and multiplied by the number of minutes that have passed. So basically at time 0, there are going to be 100 gallons, but at time 1, they're only going to be 99 gallons, and then 98, and then 97, because we're allowing liquid to come out at 1 gallon per minute. So every minute, there's going to be 1 fewer gallon inside of there, so the concentration will be however much sugar is in there divided by however much water is in there. We know that the rate at which water flows out is 1 gallon per minute. We need to keep pounds per minute as our unit. So we multiply the numerators, you get y pounds. We multiply the denominators, you get 100 minus t minutes. The units of gallons cancel out. So our differential equation then is the inflow rate minus the outflow rate, which is simply p minus y over 100 minus t. So now we're going to begin solving this, and since this is a first order linear differential equation, we can use the method of integrating factors, and we know that our a of t is the coefficient of y. Okay, so in this case, there's technically a 1 there. So the coefficient of y that I could write out is negative 1 over 100 minus t. And the coefficient, and the constant term is really, if I put the plus p over here, then that's what we call our b of t. That's what we call our a of t. So in the next step, our goal is then to say, okay, well, we need to integrate e to the negative integral of a of t dt to get our value of mu, our integrating factor. Now, depending on which technique you use, if you use substitution or you use a computer algebra system like Wolfram Alpha, you might get a slightly different answer. And this may create some confusion because when you use substitution, you're likely going to get 1 over 100 minus t. So you get e to the negative integral of that. Sorry, there should be a negative sign there. E to the negative integral of negative 1 over 100 minus t. You get a natural log, you get an e to the natural log, you end up getting 1 over 100 minus t. Using Wolfram Alpha, it will output 1 over t minus 100. And clearly, these are different, right? These are not the same. 1 over 100 minus t is going to be the exact opposite of 1 over t minus 100. So if you rewrite this and you factor out a negative 1 in the denominator, you'll see that this is really just 1 over negative 100 minus t. And so that's going to be the same value, but the opposite sign. So which one do we use? Well, it turns out it really doesn't matter, but we have to be very careful about using our correct signs. So this is our integrating factor solution, 1 over mu times the integral of mu b. And so if we do this using our substitution method, then our mu is 1 over 100 minus t multiplied by mu, which is 1 over 100 minus t, times b, which is the unknown flow rate. And now we can do some reduction here. So p is a constant in terms of t, so I can factor that out. 1 over 100 minus t is simply 100 minus t. And then the integral of 1 over 100 minus t is the negative natural log of 100 minus t plus c. So you can do that again using substitution if you like. I've got a negative sign here. I can do a couple of different things. Let's see, did I do anything? I don't think I did anything in that step right there. But so far, so good. So what I'm going to do here is I will distribute the 100 minus t to both the first term and the second term. So p times 100 minus t times negative natural log of 100 minus t will give me negative p 100 minus t times the natural log of 100 minus t. Distributing it over to the plus c, I get c times p times 100 minus t. And finally, what I can actually do here is so here I have this negative sign here. This is really a negative 1. I'm going to distribute that in here, and that allows me to make the 100 negative and make the t positive, so I get t minus 100. And then what I'm going to do to make this term look the same, as you'll see, we'll get the same answer. What I can do here is I can actually factor out a negative 1 from the parentheses here and make it t minus 100. But because c is an arbitrary constant, negative c is the same thing as just saying plus c. So that's the answer that I get by using substitution. Now using our Wolfram alpha answer, we get 1 over t minus 100, but so is this, 1 over t minus 100. These are the same mu's. So when we do that, we now get, again, factor out p times t minus 100 times the natural log of t minus 100 plus c. Notice that we don't get a negative sign like we did back here because the negative is due to the fact that we have a negative 1 in front of our variable, but here we have a positive 1 in front of our variable. Therefore, we don't actually end up with a negative sign inside of here. And this is the absolute value. So keep in mind that this and natural log of 100 minus t will produce exactly the same result because the absolute value of, say, 5 minus 100 is the same thing as the absolute value of 100 minus 5. Remember, absolute value just takes the positive version of that number. Next, what I'll do is I'll distribute, like I did in the step over here. I'm going to distribute p times t minus 100 to that term. I'll get that piece right there. Distribute it over here. I'll get that term right there. And now let's see, what did I do here? I don't think so I have a minus. I don't know why I have the minus. Sorry, that should be a plus. But nonetheless, it doesn't matter because I have arbitrary constant, so that negative 1 can combine with the arbitrary constant. And now what I notice is that these are actually exactly the same, right? Because I have t minus 100 here, I have t minus 100 here, I have t minus 100 here, I have t minus 100 here. Here I have 100 minus t, here I have t minus 100, but because that's part of a natural log, it's the absolute value, these two quantities will produce the exact same result after taking the absolute value of that. So I get the same answer no matter what, no matter which version of integration I use, even though the integrating factor is different. The question I wanted to answer is what value of P should I get in order to, after, there are only 5 gallons left, in order to have a concentration of 0.5 pounds per gallon? Well, first of all, I need to solve for my C, my arbitrary constant, because I have 4 variables in this equation. I have Y, T, P, and C. C is one that I can take care of because that's part of my initial condition. And so I'll plug in, I know that if there are 0.25 pounds per 1 gallon, and there are 100 gallons, that means there are 25 pounds in the 100 gallons. So I get this ordered pair here. Plug in 25 for Y, 0 for T. Do some reduction on that. 0 minus 100. Now that's going to give me negative 100. Natural log of 100 minus 100, which is the minus 100 that comes from here. And now what I'm going to do is I'm just going to isolate C. So I've divided both sides by negative 100. Negative 100 here and divided by negative 100 here. And then next thing I've done is I've subtracted P, ln 100 from both sides. So I'm trying to isolate C. And the next thing I do is just divide by P here and divide by P over on this side. And I get C equals that. So what I'll do is I'll go ahead and just replace my value of C. So that's C right there. Remember from a couple slides ago, that's this value of C right there. It looks messy. It has to be in terms of P because I don't know what P is yet. What I do know is that I want to have, when there are 5 gallons left, I want to have a concentration of 0.5 pounds per gallon. So because I start off with 100 gallons, right? I start off with 100 gallons, but each minute I lose 1 gallon, right? 1 gallon per minute. That means that it's going to take 100 minutes, or sorry, 95 minutes, right? 95 minutes to remove 95 gallons, right? It's the same ratio. It's a proportionality thing. So to remove 95 gallons, that's going to take me 95 minutes. So T is 95. 0.5 pounds per gallon means there are 0.5 pounds per gallon times 5 gallons left. That's 2.5 pounds of sugar. So basically, this gives me an ordered pair. At time 95, I want 2.5 gallons, which we can use to solve for P. So now I've got a new ordered pair. Plug in 2.5 for Y back up here. And then now I'm going to plug in 95 for time here, here, and here. And what I get when I solve this equation using technology or whatever you want to use, you get 0.08345, positive number. Again, you got to be really careful back here when you do that substitution in one of those previous steps where you do this. You know, a negative emerges here in the integral of 1 over 100 minus t, but you don't get a negative sign out of the integral of 1 over t minus 100, which makes the big difference there. So we get that. And now we also want to answer the question of, is it possible for, based on our equation, is it possible to get a, is it possible to get the last drop of water out of the bucket to have a concentration of 0.7 pounds of sugar per gallon? So the first thing I'm going to do is I'm just going to graph this. You can use limits on this, but it's much easier to just graph this function. And what I've graphed is that's our equation for the amount of sugar in there. But because I want to deal with concentration, either I could convert the concentration to pounds, or I can convert the pounds to concentrations. My numerator is the number of pounds of sugar left. My denominator is actually the number of gallons inside of there. And so what I've done is I've just put in P into Desmos.com. And what I can do here is I can actually insert a slider for P. And I can kind of just check what's going on as I change the value of P. So notice that at time 100, of course, things blow up. So ignore what happens after time 100, because at time 100, you're out of water. So it doesn't really make sense to talk about anything after 100, but it looks like for when P is 1 pound per minute, that after 100 minutes, the function just blows up. And I want this thing, this function, to have instantaneously right before we reach time 100 to have a concentration of 0.25. So I want the function to be somewhere down here. What I see as I continue to increase P, this function just always blows up. Now I can actually increment this a little bit smaller. I can do like 0.1 increments in the step size of this function. And so that kind of allows me to see, I can get real close down here, but this is not going to be much luck to try to get that last drop, right? Because even though I can get this function to really scooch down here, as you get close to 100, this function is going to blow up no matter what. Why is that? Because I'm taking 100 minus x. So at time 100, this denominator, close to time 100, this denominator is going to be really, really, really small, which means this fraction is going to be really, really, really big. So no matter how small I make this, even though I can get it probably down to that concentration for a while, towards 100, it's going to blow up. So complex question required a lot of setup and thinking and a lot of complicated integration, but that's typically the kind of question we have where we want to figure out some unknown even beyond just following the